Okay, y'all. Good afternoon. I'm doing this on Tuesday. You'll be viewing this on Thursday, I guess, or maybe earlier if you want to. But y'all, I got some fantastic submissions on this problem right here. There was a few misses, but all of y'all did your level best to approach it properly. And I was very impressed with your mathematical maturity or your ability to go to night study hall. Either way, it's good. But now, y'all, the hint on this was that you could eventually get this written as something in this form, and it sure doesn't look like it when you first a to the y squared. There, all right. It turns out, folks, and it really doesn't look like it when you first see this. All right, but you can write it. That's what makes this a challenging problem, a cut above the rest, not a garden variety, vanilla type problem. Yeah, I'm going to do my best, and I know I was screwing y'all over last time on this, to keep it on the screen. All right. Now, so again, it's rather shocking that something that looks like this can actually be written in quadratic form. Notice I'm using a different letter here because we're using x as our exponent. Okay. Now, 2 times 3 is 6, so you can write this as 2 to the x times 3 to the x. And a number of you did this just fine. I'm not trying to do this for the whole group. But anyway, I just wanted to show it because there were a few of you that kind of got lost on it. Now, this would be, right over here, this is 2 to the x to the 2, you see? And now you're going, oh, hell, there's a 2 right there, isn't there? Okay. And then right here, this is, if you bring this to the other side, this would just be using laws of exponents, 3 to the 2x, even though technically you don't even have to reduce it down like that. Okay. Now it becomes really, really clear. And I'm not going to work this whole thing out. I just want to make sure you guys, I'm going to get it set up and then you guys can kind of finish it off because we still need to finish the angle lesson. But in any event, if you allow for the substitution y equals to 2 raised to the x, okay, and bring him around to the front, you actually get y squared plus 3 to the x y. Now that's kind of weird. You're used to a number being right there, right? But that's not the case here. And then finally we have minus 3 to the 2x equals 0. Now, y'all, what makes this fly is this part right here that you would normally expect to be a number is your c right here, right? Okay? And then this part corresponds to this part, and then this part right here corresponds to this part. All right? Now, what we know right here is that since y is equal to 2 to the x, we can use the quadratic formula to write this as 2 to the x, right? Call it y or call it 2 to the x. It's easier just to get this written down right now. Is equal to negative b. Well, this object right here is your b, right? This is your b as far as this goes. So that's going to be equal to minus 3 to the x using the quadratic formula. And this is the hardest part, is just you're so used to seeing x or something in here, and it's not happening that way. Okay. Now minus, so b squared, well, this is your b, so that's going to be 3 to the 2x if you square this quantity. Okay. Now I could show one more step here, but I don't really think I need to. There's a 1 there, so that's minus 4 times 1. I'm doing it there. It's superfluous, but I'm just putting it there. One of my favorite words, and somebody else used it in a correspondence with me. Superfluous means overflow, excessive. All right. Mellifluous means sweet and flowing like honey. Okay. We need some of that, don't we? Now, so y'all, you have minus 3 to the 2x there, all over 2. Now, y'all, from there, and a few of you got this, I think, from here, and I was quite impressed. But it turns out you can factor the 3 to the 2x out, and it'll make it 3 to the x. And anyway, when you do all the algebra on this, folks, the only answer is circa, and I'm just going to write down, yeah, I prefer to see the exact form, but it ended up being circa 1.18, okay? And those of you that sent in the graphs, 2 or 3 of you, I think Brendan, who else? Daryl, a few of you got this other guy, big tall guy in the front row who really likes Dr. T-Cat. What's that guy's name? Anyway, but a few of you guys got this, all right? And I just don't have time to write it all out. This corresponded to where the two graphs crossed if you put into the calculator or your graphing software. So, y'all very good on that, and I appreciate you guys being willing to take on a challenging problem like this, okay? Now, so let's move along. Let's move along. Try to keep this video manageable. Okay, y'all, this is where we left off last time. Now, folks, remember the result. What's going to come in handy here, folks, today is we're actually talking about angular speed versus regular linear speed. We're going to relate the two things together, spend a little bit of time on that. But do recall that here's the connection. If you have a circle, and today it'll be useful to think of this arc length as being in motion. So I'll just draw this like this right here, okay? So this is R right here, the radius of the circle. S is the arc that subtends this angle theta. Subtends, another cool word. Then not in common parlance, but it's a math word. And the relationship here is theta equals to S over R. All right? And so you see just that's the connection. If theta is measured in radians, this is true. Now, another way to write this, and I think we did this last time, is you can write this as also R theta equals S, right? And that would be useful if you, of course, God, I hate it. Man, I always got to watch that. It doesn't quite fit where it's going to be readable. And, I'm going to see if we can go this way. Hopefully you can see it. I can see it. Okay. This is useful right here if you know the radius and the angle. All right. And then if you know the radius and the angle, you can get the arc length. All right. But it's also useful to think of this S as moving around. Okay. It's static right now. But think of the S as moving around, and that gives you what you call an angular velocity. But S is still a linear distance if you straighten out that curve, right? So S is still a linear distance. And so velocity or speed is the same as linear distance divided by time, right? So this is called linear speed. It's even though it's moving on a circle, you could flatten it out into a line, right? Okay. Now, so what we want to do is relate that. We want to relate that to angular speed. Now, angular speed is no different other than you're measuring the rate that an angle is changing. For example, like 1 revolution is 2 pi radians, right? Equals to 2 pi rads. So if I wanted to say 3 revs per minute, okay? 3 revs per minute, that's awful slow, maybe a Ferris wheel. 3 revs per minute, that's the same thing as saying 6 pi rads per minute, okay? That would be an example of angular velocity, right, folks? Hope you guys can see that. Damn it. Okay. So 6 pi rads per minute. I'm going to take a chance here, folks. Okay. I think it looks a little bit better once it's actually, recorded and stuff. But this is an example of omega. That's an example of, and I'm going to do my best not to make it look like a good old Caucasian W, okay? But that's omega, folks, and that stands for angular speed, okay? Angular speed. And this is just an example. 1 revolution is 2 pi rads, or 360 degrees. So 3 revs is 3 times 2, which is 6 pi here, right? So that's an example of an angular velocity, okay? Now, so let's go ahead and make sure we see why this and this are related. This is the relationship. This is the so-called relationship between angular velocity and linear velocity, okay, which you may have seen in physics or somewhere already. And so, but what we're going to do, folks, is actually write down what we know to be true just by definition. Okay. Velocity is equal to distance divided by time. S is just a curvilinear distance, right? So we have S over T, right? But you see right over here, S is good. It's still on the screen. I'm not pointing to nowhere like I was, I think, with y'all last time. I'm pointing to something that you can see. That's nice. All right. So, folks, right here, you're going to actually rewrite this as R theta over T, right? Folks, I physically replaced S with what it's equal to. And sometimes in math, that's all that happens. Half of math is being organized and just doing substitution. All right. But we already know that omega is defined to be this. So you see that's R times just fraction manipulation. Okay. But that's equal to R omega, right? So again, folks, the connection between angular velocity and linear velocity is this simple looking result right here. And just get used to this Greek omega, the W, the curvy W, the omega. That is not linear speed. That is angular speed. And we've seen an example of angular speed. Been on a merry-go-round, you know what angular speed is, especially at the top with your girlfriend, right? You want it to go real slow up there, right? Right? Okay, I didn't say that. All right, now, so folks, so this is the connection between velocity, angular velocity, and the radius. So let's take a look at this one right here. All right. A child is spinning a rock. Oh dear, where are his parents? A child is spinning a rock at the end of a 2-foot rope at the rate of 100 revolutions per minute. Find the linear speed. We see, y'all, this is a very, very straightforward process. We already know it has to be 2 feet right there, right? And that's kind of cool just to write down what you're doing right then and there. If you read this, that this would be the same. Don't make me draw the picture, but that's a radius of 2 feet, right? All right, that's the end of the rope, and his little hand, uninjured hand at this point, is where the rope starts, right? All right, now what is omega? We need omega, and y'all, I'm going to write this as a work in progress. Right now, we don't quite know what omega is, do we? Okay, but we do know that one rev is equal to where are we on the time? Yeah, it's 11, 12 minutes. Okay, 1 rev is equal to 2 pi revs, right? And y'all, it's so common for people to do this, forget to do this conversion. So that means that omega has to equal to 180 times 2 pi. And y'all, you can drop the rads. It's dimensionless, like I told you the last time we assembled. We never assembled, did we? When we assembled in cyberspace, and I was doing all the talking, right? But so y'all, this is equal to 360 pi. And y'all, I should have been writing in, but that's rads per minute. I should have been writing that in above, but we'll just leave it like that, okay? So here we go. Linear velocity is 2 feet times 360 pi rads per minute, right? Now, y'all, you kind of see why I made a big stink and got all excited about radians being dimensionless, right? See, if radians had any dimensions, it would screw up what we know the answer has to be, right? The answer has to be in feet per minute, right? And so the fact that radians has no dimensions lets us carry right on like we didn't even notice it, right? So that's equal to 720 pi. Now all of a sudden it changes to feet per minute. And I'm normally not a stickler on this, but make sure you show me your units. Okay, it is important. And I stayed on the screen the whole blasted time. Okay, y'all, this is totally fine. No need to use a calculator. All right, now let's move along here. Y'all, this next one I'm going to show you is kind of a standard problem. You got the double pulley system going on right here. Now, what we do know right here, folks, even though the pulleys are different, the linear speed has to be constant, right? Unless this chain, or is that a chain or belt? Yeah. Unless that belt is slipping around, we know that the V is the same, right? And this is just so obvious that it hurts, but it does come into play. V is the same on Okay, V is the same on both, or those pulleys, yeah, on both pulleys. And again, yeah, really, duh. Okay, on both pulleys. But what's different here, of course, and they don't spell it I-E-S. Okay, you put an S at the end there. Sometimes it's IES, isn't it? All right. So V is the same on both pulleys. V is the same on both pulleys. And so what that means is we're going to have two different statements here. I'll just use big and small if you want to. So remember that V is equal to R omega, like that. V is equal to R omega. But V is the same, so we got two different angular velocities, right? Obviously, this angular velocity is going to have to huff and puff a lot more than this, right? All right, just common sense, bicycle, 10-speed bicycle, tell you that, right? Now, so y'all, what's going to happen here is we're going to set, now which one are we looking for? Okay. Y'all, I'm going to keep it under 20. I'm pretty lucky I can keep it under 20. All right. The 2-inch pulley is caused to rotate at 3 revolutions per minute. Okay. So that means that, let's do it like this. We're going to have 2, right? And y'all, it's inches, okay? So it's a hassle to write that down. So everything's in inches, right? So this is 2 inches. I won't write it down just to avoid clutter creep. All right. And so this is 2 inches. Now, your omega, what are we trying to find? Determine the revolutions per minute of the 8-inch pulley, right? So here's what we know, folks. The omega for the 2-inch pulley is 6 pi, right? Okay, and that's radians per minute. Everything's in minutes, so I don't mind you guys leaving this out. It's cool. All right, everything's in minutes and inches, right? So we can just leave that out. So y'all comfortable for this is the circumstance for the small one, right? Read it one more time. The 2-inch pulley is moving at 3 revolutions, but 3 times 2 pi is the 6 pi you see right there, right? Now, so that's a statement of velocity, right? That's a statement of velocity. But since the velocities are the same, we have to set it equal to the unknown circumstance here, which is going to have an 8 right there, right? And then what's your unknown? It'll be omega for the big one, right? And you can just call it omega here since we've already resolved this over here. So determine the revolutions per minute of the 8-inch pulley. So y'all, now what we're going to get it in radians, right? And we'll have to do what? Divide by 2 pi to knock it back down to revolutions, right? So we'll be dividing this by 2 pi to get the RP minutes, right? Revolutions per minute. So, my goodness gracious, 12 divided by 8, this looks like 3/2 pi right here. Can y'all verify that for me? Verify that for me. God, we're doing so good on time today. It won't take as long to upload this to YouTube today. All right, so omega, right? Good there? Okay. Now remember, just like we multiply this by 2 pi to get RPM, we have to divide this by 2 pi to get revolutions per minute, right? So the revolutions per minute, and I'll write this down, folks, revolutions, and it's not RPM like revolutions per mile, revolutions per minute, right? I'll do it. Revolutions per minute would be equal to this divided by 2 pi, right? All right, folks? So you see here, that's equal to, the pi's cancel, folks, and I get 3/4. Okay, that seems pretty small. But you know what? It's the larger one, right? And it's not really going that dang fast, right? 3 revolutions per minute is pretty friggin' slow, right? So that makes sense, folks. That's believable, right? This is a slow-moving sucker. It's a small, slow-moving thing, right? So this is a bigger one. It's going to move even slower, right? So, y'all, this would be the answer, okay? 3/4. All right, folks, there will be an assignment. There'll be one problem. It'll be posted in Canvas. It's something kind of like this problem, I guess, sort of. But anyway, that's all I have for you today. Just keep your eyes on Canvas, and you'll know exactly what to do in terms of your assignments. I appreciate you working hard, and almost all of you are staying on top of it, and I do appreciate that very much. Have a good one. Go Dodgers.